Mid-ocean ridges and seafloor spreading. In the mid-1900s, scientists mapped the mid-ocean ridges using sonar. Mid-ocean ridges curve like the seam of a baseball along the sea floor. They extend into all of the Earth's oceans. This figure shows the location of these ridges. Most of the mountains in the mid-ocean ridge system lie hidden under hundreds of meters of water. But in a few places, the ridge pokes above the surface. For example, the island of Iceland is part of the mid-ocean ridge that rises above the surface in the North Atlantic Ocean. A steep-sided valley splits the top of some of the mid-ocean ridges. In 1960, Hess proposed a radical idea. He suggested that a process he called seafloor spreading continually adds new material to the ocean floor. In seafloor spreading, the seafloor spreads apart along both sides of the mid-ocean ridge as new crust is added. As a result, the ocean floors move like conveyor belts, carrying the continents with them. This figure shows the process of seafloor spreading. Sea floor spreading begins at a mid-ocean ridge, which forms along a crack in the oceanic crust. Along the ridge, molten material that forms several kilometers beneath the surface rises and erupts. At the same time, older rock moves outward on both sides of the ridge. As the molten material cools, it forms a strip of solid rock in the center of the ridge. When more molten material flows into the crack, it forms a new strip of rock. So some evidence for seafloor spreading. Several types of evidence have supported Hess's theory, but we're just going to look at a few of them. Eruptions of molten material, magnetic stripes on the rock of the floor, the ages of the rocks themselves. The evidence led scientists to look again at Wegener's hypothesis of continental drift. So in the 1960s, scientists found evidence that new material is indeed erupting along the mid-ocean ridges. The scientists dived into the ocean floor in Alvin, a small submarine built to withstand the crushing pressures of 4 kilometers down in the ocean. In the ridge's central valley, Alvin's crew found strange rocks shaped like pillows or toothpaste squeezed from a tube. Right here. These rocks form only when molten material hardens quickly after erupting underwater. These rocks show that molten material has erupted again and again along the mid-ocean ridge. Evidence from magnetic stripes. So Earth behaves like a giant magnet with a North Pole and a South Pole. Quite surprisingly, Earth's magnetic poles have reversed themselves many times during Earth's history. The last reversal happened about 780,000 years ago. If the magnetic poles suddenly reversed themselves today, you would find that your compass needle pointed south. Scientists discovered that rock makes up the ocean floor lies in a pattern called magnetized stripes. These stripes hold records of reversals in the Earth's magnetic field. The rock on the ocean floor contains iron. The rock began as molten material that cooled and hardened. As the rock cools, the iron bits inside line up in the direction of the Earth's magnetic poles. This locked the iron bits in place, giving the rocks a permanent magnetic memory. Using sensitive instruments, scientists recorded the magnetic memory of rocks on both sides of the mid-ocean ridge. They found that the stripes of rock that formed when the Earth's magnetic field pointed north alternated with stripes of the rock that formed when the magnetic field pointed south. This is a figure that shows that. Notice that the pattern's the same on both sides of the ridge. The final proof of sea floor spreading came from rock samples obtained by the drilling into the ocean floor. The Glomar Challenger, a drilling ship built in 1968, gathered samples. The Challenger sent drilling pipes through water of 6 kilometers deep to drill holes into the ocean floor. This feat has been compared to using a sharp-ended wire to dig a hole in a sidewalk from the top of the Empire State Building. Samples from the seafloor were brought up through the pipes. Then the scientists determined the age of the rocks in the samples. They found that the further away from the ridge the samples were taken, the older the rocks were. The youngest rocks were always in the center of the ridge. This showed that seafloor spreading has really taken place. So here's the math. I know everybody loves the math. There is a little bit of math that we're going to be doing. It's simply doing the rate of seafloor spreading. So the example that I'm giving you here is that we're going to assume that the ocean began forming around 120 million years ago, and it's been spreading ever since. The distance from the crest of the mid-ocean ridge to the nearest continent is 2,400 kilometers. So we want to know what the spreading rate is in centimeters per year. So 1 kilometer, if we break it down into centimeters, because that's how I need to see it in centimeters, it is 100,000 centimeters, or 1 times 10 to the fifth in scientific notation. So we have 2,400 kilometers. If we convert that, it's 2.4 times 10 to the third kilometers, or 2.4 times 10 to the 8 centimeters. This is what we're going to be using. 120 million years ago, in scientific notation, comes to 1.2 times 10 to the 8th years ago. So simply, when we want to do the rate, we take the distance, right here, 2.4 times 10 to the 8th, and we divide it by the age difference, 1.2 times 10 to the 8th, and we're going to come up with, sorry, you can't see that, can you? 2 centimeters per year is what we're going to end up with. So this ocean ridge is moving at 2 centimeters per year. So we want to know whether they're slow, intermediate, or fast. So in the Atlantic Ocean, the Mid-Atlantic Ridge is a slow spreading. In the Pacific, the East Pacific Rise is a fast spreading. So in the Atlantic, we're going to be looking for rates around 1 to 5 centimeters per year. That would be what we just did at 2 centimeters. It's a slow spreading rate. Intermediate rates are between 6 and 9 centimeters per year, and fast rates are around 10 or greater centimeters per year. All right, on to work.